All right, welcome everyone. So we have 400 registered for the webinar, but we are around 144 right now. People are still coming in, but nonetheless, I think we should get started. So thank you so much for being here today. I'm very excited. I hope you are too. I'm very glad to be continuing the top webinar as host and organizer with most of the old team supporting me in the background here. And we have some great things planned, and the first of which is this lecture series on the basics of density-based topology optimization. Later this year, I'm working on that we will have the equivalent for the level set methods, and then we will also have some different other types of webinars. More information on that will follow continuously and will be posted on our website and sent out via the mailing list and other channels. Currently, there are some issues with the current website, but we are working on a solution, so hopefully that will remain updated in the future. The recording is currently live on YouTube and will be available there later also. And for the future, we are looking into China-friendly options also to post the videos on. So that was the sort of general introduction. And now to the introduction of the man of the hour. So the esteemed Professor Ole Sigmund will give us the first of 3 lectures today in the basics of density-based topology optimization. I think he needs no introduction, and if I were to do it justice, it would take half of the hour that we have today. So I will try with a short one. He's been working on topology optimization since the early 90s, and he's the inventor of the sensitivity filter, pioneer of inverse homogenization and mechanism design, and many other things. He is one of the main reasons that TO, topology optimization, has become so popular and broadly applied, and that's been through his work and the freely available codes and apps that Ole started. The lecture will be around 50 minutes, and then we will have some time for questions afterwards. And please use the Q&A function. So at the bottom of your screen, you will see a button with a question mark and Q&A. Click on that and you can submit your question. You can do that during the lecture, and then we will take the questions at the end. And if there are many questions, then Ole has kindly agreed to hang around a little bit beyond the hour that we have scheduled. And I think with that, I won't take any more time. And now we are almost 200 and about 10 or 11 online on YouTube. So that's pretty good turnout. So with that, Ole, please go ahead.
Thank you so much, Joe. Thank you for the introduction, and thank you for taking over the webinar organization, and thank you for inviting me to give this sort of introductory lecture. I've heard a little bit about the spectator lists, that there are many experts in it, but also beginners. So it's also a little bit challenging to satisfy everybody, but I think even if you are an expert, there should be some good advice in this talk. And if you are a beginner, I hope I will sort of give you an insight into the background of topology optimization and all its wonders. So let me start by showing some pictures that you can find on crawling the web, and you will see these fantastic looking structures that are used both in Formula One but in other high-end products with the aim of saving weight and making fancy designs. But our method, the topology optimization method, has also been or is being applied to more everyday cars and consumer products. One example is industry providing softwares for designing mega castings that can save a lot of parts in the car industry and being manufactured in one piece in gigapresses and stuff like that. So the method is being used everywhere for small products and larger products out there. In parallel, in research, I'm showing some examples from my own research group. We are trying to extend it to all kinds of other areas in multi-scale structures, hierarchy, multiphysics, optics, acoustics, and you name it. So the state of the field is extremely advanced, and it's a pleasure to see how many applications there are of this basic method of distributing material that we also call the density approach. Now, this was sort of the state of the art, but let me start this introduction to the area by going all the way back in time. So I could go back to the Roman aqueducts and stuff like that, but actually I will start with Michel, who lived in the beginning of the last century, who started these beautiful structures that we know and you see in different situations. So Michel's work in the early 1900s was taken up by many clever researchers in the 60s and 70s and doing beautiful works where people could actually find analytical solutions to rather complex problems. And then with the advent of the computers in the 60s and early 70s, well, people started experimenting by letting the computer and the finite, well, not the advent of computers, but rather the advent of finite element analysis that was based on computers. Then people started playing around. So there were early works on truss topology optimization. And actually the first works on what we later call the variable thickness sheet problem were also done in the 70s and the 80s. Then a big development happened when Professor Gengdong Cheng joined Niels Olhoff as a PhD student in the 80s, and they looked at optimizing plate structures, so actually optimizing the rib distribution to maximize the stiffness of plate structures. And they discovered that if they had a finer and finer mesh, then they would get more and more ribs. And so, in other words, they discovered that there was a mesh dependency, or you could also say there was not existence of solutions. Because the finer you made the grid, the finer the structure, and it meant you would never be able to come up with a solution because you could just refine it. So this observations then led, or in parallel to that, led to composite theory and clever Russian and French applied mathematicians who came up with theory for finding optimal composites layered at different layers that actually could predict optimal structures. And so this was sort of the state of the art when someday on a beach in Portugal, two young researchers, Noboru Kikuchi and Martin Bensu, were put together by clever people in the background. And they were discussing the state of the art in the field and were thinking, couldn't we put this together and make an optimization method that used the insights of optimal composites to design structures and thereby achieve mesh or mesh convergence. And so that led to the very first work on topology optimization, or rather the homogenization approach to topology optimization. And so in the very first work with Bensu and Kikuchi, they used a so-called rectangular hole structure that oriented the material along the principal stress directions and adapted the thicknesses to the local stresses. Then in a second work, Martin Bensu also introduced the layered optimal microstructure, and that led to the results that we know today as the homogenization approach to topology optimization. Actually, if you go back and read the paper by Bensu, apart from the two methods he compared in his 89 paper, then he also suggested a third approach, which he called the direct approach, that used what he called artificial density interpolation, rho to the p, where rho was the material relative density and p and penalisation power. And he used that and said, well, this is a reference, it's interesting, but it's not physical, but we suggest these homogenization approaches. And so actually this density approach, which would be the topic of the 3 lectures essentially, I will come back to some of the multi-scale in the third lecture. However, the density approach was later coined the SIMP approach, simplified isotropic material with penalisation, by Rosvani and Ming Su in their paper from 1992. So this was sort of the status. This is the very early days of the field. These pictures that Bensu and Kikuchi created were sort of looking a little bit mushy. So luckily, clever people and foreseeing people like John Rasmussen, together with Bensu and Olhoff, they said, let's interpret these structures and then make a post-processing using shape optimization. And that paper here, 91, was actually the one that introduced this MBB beam that we have been using as a reference benchmark case since then. And I think with that paper, it's sort of the popularity started, and more and more people started using different or developing different optimization methods. And so if we look today and again browse the internet, we will see myriads of beautiful organic looking structures that are optimized, I would say, with topology optimization. But if you read the papers, there would be all kinds of other names of that, bionic design, evolutionary methods, nature-inspired design. But really, they come from the same source. First, the homogenization approach, and really the density approach is introduced back in 1989. So this was sort of a little bit of the introduction. And so in my talk, I'm going to be talking about the density approach and getting into the details about that. If you are interested in other topics, then actually Kurt Mauder and I wrote a review paper where we said, well, there's actually not that much difference between the methods, like density-levelset, topological derivative, phase field evolutionary. They have many names. Essentially, they are doing the same with small differences in them. And we are reviewing and discussing that in this paper. But in this talk, I'm going to focus on the so-called density approach. And as alluded to already today, I'm sort of starting with the basics. In February, I will talk about more advanced filter and geometry control and randomness and robustness and stuff like that. And then in the last talk, end of February, I will go full circle and actually show how the density approach is getting back into some of the multi-scale or homogenization-based approaches that started already many years ago. So let's get going with the basics of the density approach. And I'm an engineer. I'm going to present it in an engineering way, so not too much mathematics, but I'm sort of assuming that people at least know basic finite element analysis to be able to follow the following. So I'm starting with a design domain that has been discretized by finite elements. It may have some supports, it may have some loads, and everybody working with finite element analysis should know the finite element equation. We have K, the system matrix or the stiffness matrix in mechanics. U is the state vector, that would be the displacement solution, and F is the load vector. Now we're going to introduce some design variables here, and the basic idea is that in every element in the mesh, we introduce a design variable that can take values between 0 and 1, so that would be a relative element density. If it's 0, there's no material. If it's 1, there's solid material. And that means that the element or the global stiffness matrix can be assembled over each of the local elements times some function where we model the Young's modulus as a function of this density. For now, I'm not going to exactly specify how I model this density, but just say that the Young's modulus of 0, so no material, that would be a very small value. And the Young's modulus of density 1 will be the solid material. And this very small value, we could put it to 0, but then you would have to remove the elements. To make efficient schemes, we actually work with what we could call a fixed grid, but we give those void elements a very small stiffness such that we don't get ill conditioning of the stiffness matrix. So this is an essential design problem. Then we can formalize it a bit more and say we want to minimize some function of both the design variables rho collected in a vector and the state vector, which indirectly will be a function of the densities here. And then for now, the simplest problem we could imagine is just putting a volume constraint, where the volume is a sum over the elements times these element densities. Now, this is a very fundamental formulation. We could, and we will later on, extend it, so we could add additional constraint values that again could be functions of the state or the densities. We could add as many as we like, and the things would sort of work in the same way, but we would need a better optimization module for it. Today, I'm actually going to fairly much stick with the original problem and actually make it even simpler. So I'm going to consider the famous compliance minimization problem. So our objective function is force times displacement, work of external forces. We want to minimize that. It's also the same or similar to maximizing the stiffness of the structure. So this is the problem we want to solve. And now the question is, how do we formulate an efficient procedure that can solve this for very large number of design variables? So in other words, if we took the MPP being from before, and we want to see some optimization that efficiently distributes the material to come up with an efficient design, and this method should also be able to handle many design variables, I'm sort of advocating we shouldn't do problems with less than 10,000 variables in 2D, and we should be beyond 1 million in 3D. Otherwise, it doesn't have practical value what we are doing, and it doesn't really model the physics of the real systems. So this would be in 2D. In 3D, I have this jet engine bracket example. Here we discretized it with, I think, 10 or 12 million elements. That's maybe overkill. But again, 1 million elements is something we want to do. So how do we solve a problem with 1 million design variables to optimality? Well, some of the approaches would be, can we solve an integer problem or a discrete form of the problem? So we only allow the design variables to be 0 and 1, so every element should either be void or solid. This, unfortunately, is a very hard problem. Partly discrete problems are very hard in themselves, but also the solution of the problem. So for every test we want to do of computing the displacements and the objective function for a design variable distribution, it's a very expensive PDE solve or finite element solve that we have to do. And if we look at the number of combinations, you want to fill P out of n elements in the discretized structure, well then even for ridiculously coarse meshes with 100 elements and 50 to be filled, we have astronomical number of design variables. So it's really not possible to test them all. Some people have in times, and also still some are doing it, tried to solve these problems with genetic algorithms or simulated annealing or other algorithms that I would call non-gradient topology optimization. And there are some misunderstandings in that field. If you read the papers, they would say that they use global search and hence converge to better optima, but that's a misconception. Global search does not guarantee that you converge to the global optimum, just that you search everywhere. You get discrete designs. As you will see, we can get discrete designs by other more efficient means, that you don't have to find gradients, but actually they are really easy to implement and compute. And also that you have parallel computers, so it scales perfectly. And I would say that's a crime. You shouldn't use large parallel computers to solve problems inefficiently. That's a waste of resources. So I wrote a paper back in 2011 to advocate against use of such algorithms. And actually, I also used an example. So I looked in the literature. There was a non-gradient approach that claimed that they got the global optimum. I tried to take our efficient algorithms and then threshold it at the end, and I actually beat it. And the big difference is this is only 72 variables. They used 16,000 evaluations, and the gradient-based used 60. So really, there's no reason, or people should really not use non-gradient approaches to topology optimization. But then, how would you say, how do we then solve it? Eventually, we are going to solve problems with 1 billion elements, like in our wing structure, or maybe even 2 billion elements that we used in our bridge structures. How can you do it? Then people would say, AI, machine intelligence, whatever you call it here. And I have some opinions there also. I am skeptic, as probably many know, and I think people out there also share. So I found one paper. This is not for solving topology optimization problems, but for solving PDEs in general within fluids. And there was a Nature Machine Intelligence paper last year, or 2 years ago, it's actually already, where they were sort of criticizing the field because many of these papers out there are sort of exaggerating the benefits of machine learning. And so they were saying that some of these claims were based on weak baselines, so comparing to inefficient or badly converged reference designs, and also that many people reported more positively than was actually desired. So I share that, and this is also what I see in topology optimization. I've really not seen any very convincing topology optimization approaches in the many papers out there that use machine learning yet. So why is it so difficult? Well, this here is a reference to some older works, but really we have very varying boundary conditions, right? So here I'm just showing a simple square domain, and this is typical that people are training their networks on simple rectangular domains, but reality is 3D and it's complex geometries and many constraints and stuff like that. And loads will be different. They will be forces, they will be eigenvalues, buckling and stuff like that. So just training such networks is an immense task and costs immense simulations. Another thing, or two other things, is partly that the designs are very depending on local details. For the untrained eye, that this would both be some truss structures, but here in the right one, you have a hole in the structure, or you remove 2 pixels, which means that it doesn't work at all as extended. So it's extremely sensitive to very small variations in the designs, and also small variations in the loading direction can result in widely different designs. So it's not a nice problem to interpolate. But probably the most important part is that machine learning is mostly about interpolation. Interpolation between the training data, and the further you get out in the extremes, the sparser the training data and the worse it gets. And in fact, we are in optimization, so we don't want just to interpolate between existing designs. We want to make new and extreme structures, and there's no data available when you go out there. So these are some of the reasons why I personally don't think that solving the direct problem with topology optimization, with the AI makes much sense. We have a review paper on this where we are discussing these things. We tried to categorize approaches in various ways, and right now I'm talking about this direct design, substituting topology optimization with trained databases. And we categorize those in a generality score. So how sensitive was the result towards changes in boundary conditions or physics or other things? And then we define this break-even threshold. So how many optimization or designs do you have to make based on your trained database before your cost in training the database have been paid? And I would say that everything in the pink area of this curve here doesn't really make much sense if you're solving sort of arbitrary various topology optimization problems. However, if you are a manufacturer, for example, living of selling shoes, and you want to adapt the stiffness of the shoes, the nonlinear stiffness of the soles to individual customers, then it definitely may make sense that you do 100,000 evaluations of various microstructures, and then afterwards you can use this database to interpolate, and in that way get designs that fit the individual customer. So that's sort of my take on it. We also summarize sort of in this figure this dream scenario of substituting topology optimization with the AI is the one in red here. I said I'm skeptical on that, but it's not to say that AI can't be used for all kinds of other sub-processes and speed up things and be used. So I'm not saying that we shouldn't research in this, but we just have to be honest, and when we report, it should not be biased, and our bench lines or benchmarks should be fair benchmarks. So this was a bit of my opinion there, and of course that may be debated. So if we can't use genetic algorithms and we can't use AI, so how do we solve it? Well, the trick is we introduce continuous variables, and with continuous variables we can compute gradients, and with gradients we can solve problems very efficiently, maybe in a couple of hundred function evaluations or finite element evaluations. And so this is where this SIMP interpolation comes into play that was introduced by Bensu and coined by Su and Roslani. And this is essentially the form. We introduce this design variable, the relative density raised to some power, and then we do all the sensitivity stuff, and I will discuss it later. But this is, the key thing is we introduce grayscale, and we work with grayscale now. And then it turns out we can control this grayscale by controlling this power peak. And I will demonstrate that with a couple of examples. So again, the MBB beam, we start with P equal to 1. So there's a linear relation between density and the Young's modulus. And we run the optimization, and we see quickly the structure evolves. Black is solid, gray is intermediate, white is void. And we see now it doesn't go to black and white, but in 2D, that's fine. We can sort of interpret it as an I-beam cross-section. It's thick in the top and the bottom, and it has this shear whip in the center. So the actual optimal structure for 2D is indeed something with a variable thickness sheet that we can interpret it, where the out-of-plane thickness, relative thickness, is simply the density variable. Now, this doesn't work in 3D. We don't have anything like a thickness, so we cannot just use this P equal to 1 in 3D. And also in 2D, we may sometimes not be satisfied with this I-beam. We may have to have holes going through the structures. We may want to prefer a structure that is flat and has holes instead of variable thickness. And in that case, we can introduce P equal to 3. So now our interpolation curve, so Young's modulus as function of density, becomes this function here. And we will see if density is 0.5, we have very small stiffness. And so in that way, we make intermediate densities uneconomical, and the optimizer that doesn't have much material available will not waste the material on intermediate densities. And if we run it, we will see like this here, it quickly gets rid of the gray areas and makes this beautiful, almost black and white structure. And it's less efficient than the variable thickness sheet problem, but it's black and white. So this is the idea of the SIMP penalization scheme. And you could ask, so what is the best value of the penalization? We tried here, this is the P equal to 1 for another example. This gives us the variable thickness sheet. P equal to 1.5. Already here we start losing some of the gray areas in favor of solid and void areas. And in this case, it turns out we already have black and white solutions with P equal to 2. But the usually used value is actually P equal to 3, because in our experiences that we almost always get black and white solutions. And so this is sort of the explanation of the SIMP interpolation model. Now, as you recall, Martin Benzo introduced the method back then as an artificial material interpolation model. So you could ask the question, is it really artificial, this material law, or does there exist physical materials that follow this relation between Young's modulus and density? And indeed, Martin and I looked into that in a later paper, and we found, so there are these Hessian-Strickman bounds that theoretically predict what the optimal or the highest Young's modulus is for an isotropic material as function of the density. And that's the red line here. And we already interestingly see here the green, so P equal to 2, violates this law. So this is non-physical. And blue seems to stay below this Hessian-Strickman bound. So that is actually physically achievable. And so actually, people have shown that these Hessian-Strickman bounds are optimal in the sense that there exist microstructures that achieve them. A slightly suboptimal microstructure is the triangular hole cell that I show here, and that actually attains this curve here. So indeed, and actually we could do the analytics, and somewhat miraculously, we found that in 2D and 3D, the math turns out to say that P has to be larger or equal to 3 if the Poisson's ratio is a third in order to have physically valid material laws. And P equal to 3 was exactly the magic number that everybody used in the field up to then. So this shows that the SIMP law is actually physical as long as you have some conditions on the power P. You could also ask the question, so what does the material look like that satisfies the SIMP P equal to 3 law? And we made this sort of cartoon-like picture showing that we actually just reuse the optimal microstructures from before, but then we introduce islands to really show that the SIMP law is made sort of artificially weak compared to the physically best stuff. But it is a physical structure. And you can see how we sort of enforce that the optimizer would be stupid in using any of the SIMP law, since much of the material is just being wasted for nothing. Then you could go on and say, well, why do we actually use this SIMP law? Why don't we just use the Hessian-Strickman bound directly? Because we know there exist solutions of the Hessian-Strickman bounds, and maybe we can use that. So if we have grayscale for optimizing with the Hessian-Strickman bound, then we exactly know the microstructure that realizes this grayscale. So we tried that also, and the result is here in the green box. And somewhat surprisingly, even if we had physical microstructure, isotropic microstructure, the optimizer doesn't want it. So this is an interesting conclusion that I think many are missing, that actually if you're just optimizing compliance, then having an optimal triangular isotropic microstructure in there is not beneficial for the compliance objective. Compliance wants solid and void structures, if not variable thickness sheet, which is only possible in 2D. So this is an important observation. So this was an explanation of the SIMP law. Obviously, you can use other interpolation laws, and actually there was one suggested by Stolper and Svanberg. They actually suggested it because they could show that SIMP was not concave, so it would converge to non-optimal solutions, whereas if they used RAMP, it would be actually concave, and they would ensure that final solutions would be extreme in the sense of 0 and 1. And interestingly, if you take the RAMP law, I don't think it was intended originally, but if you put Q, which is sort of the penalization factor in the RAMP law, to 2, then you recover the Hessian-Strickman bound exactly. And so whether you use SIMP or RAMP can be up to the problem you're looking at or your preference. It has subtle differences, but I will not get into that right now. So now we have the interpolation scheme. And so this is essentially the optimization problem we have. We have some kind of, let's say, SIMP for now. We have an E-min that should be less than 10 to the minus 6 in order not to interfere too much with optimization. And then we want to solve this optimization problem. So next, this is essentially the algorithm that we are going to use for it. So we will initialize, we will perform finite element analysis, and then it says, oh, compute sensitivities. And I haven't spoken about that yet. So let's just take 2 or 3 slides for discussing sensitivity analysis. So I will just use it or demonstrate it on our simple compliance, well, actually a simple general problem to start with. We have an objective function. It's a function of the state variable, which is a function of the densities. And we have a linear finite element problem where I should say it's only the stiffness matrix that depends on density for now. I have assumed that the load vector doesn't. And our gradients, our derivatives with respect to densities, I will denote with an apostrophe. So the first way, if we want to compute sensitivities to be used in our optimizer, would just be to optimize or to differentiate directly. So phi is an indirect function of rho, so we use the chain rule. We have d phi du, du d rho. Then we look at that and say, hey, d phi du, that's easy. That's simple to differentiate. We know our objective function. But u prime, so what happens to the displacement vector if we change the densities in one of the elements? That's harder. But we can find that by taking the system equation, so that's the ku equal to f, and differentiate it, again, assuming that there's no design dependence of the load. We get this expression, k prime u plus ku prime. Then we move the first term to the right-hand side, and we see we get a solution that actually looks like the original solution. So we can reuse the factorized stiffness matrix here. And then we have a load case, which is the derivative of the stiffness matrix times the displacement vector we already found. So this means that for every design variable here, we would have to solve one extra right-hand side of our finite element problem. So that's still much more efficient than doing a head under the arm finite difference approach, but still it will also be extremely expensive for many variables. So instead, we go to the joint method, and there are many ways to explain it. I sort of take the slightly naive approach saying, and that's something you learn from the mathematicians, you add nothing to gain everything. And so the thing is, you take the original objective function, you augment it by adding some vector transpose times the solution of the original problem. And if that's already solved, then the parenthesis is 0. And so that's why I'm saying we are adding nothing. but we will gain everything. So let's see what happens. If we differentiate this, then we have the chain rule again, and then we differentiate the inner part of this. And then we see, hey, now we have two terms of these u primes, the derivative of the displacement with respect to the densities. Let's collect those, and we see here, that's this expression. We want to get this to disappear, so we want to put this to 0. And the good thing is that we can select now lambda such that this becomes 0, and that way we get rid of these unpleasant terms. And this is exactly the one we have in here with orange. That's exactly what we call the adjoint problem. So it means we have, if we reorganize, we get this, which is the adjoint problem that we solve. And again, it looks very much like the original problem. It's just transposed. We have to be aware of that. Usually problems are symmetric, so it doesn't matter, but we have to be aware of it if we have an unsymmetric problem. But anyway, it means that we just have to solve one extra right-hand side. And once that's solved, we get rid of the two red terms, and our sensitivity is simply the adjoint vector times the k prime times u. And we only need to solve one right-hand side, no matter how many design variables we have. So this is the strength of the adjoint method. It's extremely efficient, just at most one extra analysis, and we get all the sensitivities. And that's the key success of, to the success of the method. So let's just quickly see how that applies to the compliance problem that we spoke about before. So I would call this is the general formulation of the adjoint method. We solve the adjoint problem, so we have to compute the derivative of the objective function. That's simple. The objective function is f transpose u. Differentiate with u, we get f transpose. So we insert that, which means that the adjoint problem in this case is k lambda equal to minus f. That's extremely much similar to this one, just with a minus instead of a plus here. So that means that our adjoint vector in the case of a compliance objective is simply minus the solution of the original problem. And so that's nice. It means that the sensitivities become this expression, and if we write it out for the SIMP interpolation, it becomes this one. And so there are several good things about this. Well, compliance objective is self-adjoint, so that means there's no need for computing the adjoint because the adjoint is just the original solution. Interestingly, all the gradients have the same negative sign. So, and third, this term we have here is essentially the element of relative strain energy. So this is, well, you could call it a curse or a pleasure for compliance. It makes it so simple. The sensitivities are simply minus the relative strain energies. And that means that no matter what method you make, if you add material, you get less compliance, meaning a stiffer structure. And so everybody and his grand or her grandmother can actually come up with an algorithm that can solve compliance minimization problems. So that's, I think, an interesting observation here, and at very little cost. Now, just not to spend all the afternoon on this, or night, or morning for you guys out there, but I've sort of just made a little scheme that you can look up again on YouTube if you want later on, but that's sort of just to summarize how simple this actually is. So for linear analysis, I've shown you that we just need to do one extra load case for the adjoint, and then we get the full sensitivities. For nonlinear analysis, so geometrical nonlinearity, where you're only interested in the deformation in the displaced configuration, it's essentially the same. The only thing you have to solve in residual instead of the linear equation, but your adjoint turns out just to be solving one extra right-hand side for the final tangent stiffness matrix. So that's extremely convenient. And then you get the sensitivities again at very little extra cost. I also took the transient analysis case. There you want the residual to be 0 for a number of time steps, and then it turns out if you do the adjoint analysis, then the adjoint analysis is going backwards in time, where you use functions of the forward analysis as loading for the adjoint analysis. But at the end of the day, it means at most you have to solve one extra system solve, so one extra transient analysis to get all the sensitivities, no matter how many design variables you have. So this is sort of the observation here. Okay, so now we have the sensitivities, but there are still some issues, and actually I was hiding some of these issues. One thing is the checkerboard problem, and so I didn't show it in the original examples, but if we do exactly as I've described up to now, then and run the p=3 case, we see these weird structures here. And so this is essentially, you could, with a magnifying glass, you would see a checkerboard pattern, and here there's another structure, and just a short explanation for that. So we are using p=3. If we take, then the optimizer says, let me make a checkerboard. Why does it do that? Well, it's smart. So it's actually using the errors in the finite element model to cheat us. So if we look at the deformation of a checkerboard pattern visualized by this little patch of 4 elements, then the 4 node elements that we usually use, so these are linear elements, they will never see the stress concentrations in here. Actually, it thinks it's just deforming the linear edges here, and so it doesn't see any degradation of the stiffness. So if we plot the stiffness of the 4-node checkerboard patch, well, then it actually has 0.5 stiffness. So for the optimizer, it's very nice. It can have 0.5 density and get 0.5 stiffness. Why would it use grayscale, or why would it go to solid void? So this is sort of the explanation. The optimizer is using the flaws of the finite element model. So the first option would be to, well, let's use 9 node elements instead. That resolves some of it. So you will actually now have stress concentrations, and it means if you plot it in the same picture, it should of course say 9 node element here, but that's actually below the curve, and so the optimizer would not like to use checkerboards if you model 9 node elements. 9 node elements are expensive computation-wise, so therefore we are not so fond of them, and we have come up with all kinds of other methods. One very obvious one is to use what I call checkerboard filtering. So essentially we just filter in a little neighborhood. We see it as an image processing filter that removes noise, and by doing that, a small local averaging, you can get rid of these checkerboards. But we are not done with the problems yet. So we have the other problem that even if we don't have any checkerboards, then if we refine the mesh, the structure gets finer and finer. This is an observation by Cheng and Ole already originally. And of course, if you can build these, and if you can afford and have manufacturing to do it with very, very fine scale, well, then that will be the best structure. But in reality, we want fairly simple structures, and we want also to have convergence with mesh refinement such that we get, and I will show that in this picture here, that when we refine mesh, we get a better description and a better finite element model, and not a finer topology. And so just to go back here, so today there are 2 ways to circumvent this problem, either by relaxation, that's introducing microstructure and homogenization. We'll get back to that in tutorial 3. But also the alternative is to introduce restriction, as we will do today, and also talk much more about next session here. So how do we introduce this mesh independency? Well, a very popular way is to introduce what we call low-pass filtering. So we have our mesh, we put in a radius with a certain size that's fixed. Even if we refine the mesh, then there will be more elements within this radius. We call this the neighborhood. And then we can either do what we call sensitivity filtering. So we make a weighted average of the neighboring elements to compute the sensitivities. Or we can do density filtering, where we compute the average densities through this convolution procedure. And that means that we introduce a new set of variables, rho tilde, that also have to be differentiated through the chain rule. So both approaches give mesh independence, and as said, I will get much more into that in the next tutorial here. Just also to mention here, both are based on having to search for the neighborhood, which might be expensive, especially in 3D. So a much more efficient but very equivalent approach is to use the so-called PDE filtering, where we solve a kind of Helmholtz equation, which is just a scalar equation. So it's a finite element problem, but on a smaller scale than the original finite element problem. So these are the ways to introduce mesh independence and convergence. So now we have the algorithm, that we can solve and implement in our finite element procedure. I haven't discussed the optimizer, so based on the computed sensitivities, we update the design variables. There are many methods for compliance problems. We can use the optimality criteria that I will show you, but otherwise I'm a favor of the method of moving asymptotes, but there might be many other efficient algorithms that are good for large-scale problems, and I will not get into that in this lecture. So, but let me just sort of shortly, if you haven't already seen it, we have some very beginner-friendly codes out there. One is a 99-line MATLAB code. It has the full finite element analysis. It has the mesh independency filter. It has the optimality criteria solution. And essentially, this standalone MATLAB code can do most of the examples that I've shown you so far. So I invite you to have a look at those codes if you haven't already. So that was a paper I wrote in 2001. Then through the years, almost every decade, we have improved on this. So in 2011, we sped it up with a factor of 100 by pre-allocation and vectorization, meaning that this code is much more difficult to understand for the beginner, but it's also much more efficient. So definitely it's recommendable, and it has these different filtering techniques that I shortly alluded to. And then in 20, together with Federico Ferrari, we made an even more efficient code that is, I would say, even more for experts, but if you're going for speed, that's the way to go. And so apart from these three basic density-based approach codes, then there's a review paper with discussion of lots of other codes, not only for density, but for level set and phase field, and you name it. And so these codes are also the ones that are behind the famous top-up apps. Again, if you haven't tried it, I invite you to go to the App Store and download these apps and have fun and do interactive topology optimization. So I'm approaching the end, but I have still a few comments here. So one thing is, if you are new to the area, or even if you are an expert, there are so many pitfalls and so many things sort of that you should check before you compare your approaches to the existing ones. And I wrote this paper, somebody said it was quite polemic a couple of years ago, but it's full of good advice on how do you make fair comparisons, how do you do visualizations, how do you do convergence, and all kinds of stuff. And I think if you read this and follow the guidelines, then your life when getting reviews for your paper in topology optimization should be much simpler. So I don't have time to go into all these things, but I warmly recommend to read it before you submit your paper. But I do want to take up a couple of points here towards the end. One thing is, I've earlier talked about gradient-free topology optimization, but that was sort of for discrete methods, genetic algorithms, and stuff like that. But nevertheless, you will also find papers out there that claim that they do gradient-free there and do proportional topology optimization, meaning that they have a density that they adapt, but without gradients. But if you read the paper, they are saying we are actually using the strain energy as the measure of updating. And if you recall, the sensitivities that we compute are the relative strain energies. So it's not, if you have an algorithm that uses strain energies, you are using gradients. So it doesn't make sense in that to say that you are doing a gradient-free approach. Also, with proportional approaches, be careful out there. For example, there's also the fully stressed approach or fully stressed design approach. A very famous example is the L-beam example here. So with a fully stressed design approach means that you compute the stresses in the structure and then you add material where the stresses are high. And so that's very similar to adding material where the strain energy is high. And what happens is, in this case, that it adapts the material, it makes a fairly nice looking structure, but at this reentrant corner here, it will have huge stresses, and it doesn't matter, or you can't add more material at that corner because your design domain doesn't allow it. So you will inevitably be stuck with large stresses at that point. So forget about these fully stressed methods. Use a joint sensitivity analysis. And if you do that, you get these beautiful structures where stresses are nicely distributed. I should say the color scales are widely different, probably a factor of 10. So the structure to the right was optimized using the adjoint. And in fact, computing the adjoint, I think I've already alluded to it enough, but even for the stress sensitivity analysis, if we do the simple choice and say we minimize the P norm of the stresses, well then at the end of the day, we follow the standard adjoint procedure. We need to differentiate the objective function, so the P norm with respect to the displacements. That gives us a slightly more advanced expression, but still very simple. And then our element sensitivities come out of that. So it's not hard to compute gradients, use them, and don't waste time on trying to invent gradient-free methods. It's simply not worthwhile, and you get the wrong results. So that was also a recommendation. And sort of to the next steps, I still have a couple of minutes, I think. So next steps, what do you want to do after you have sort of gotten to know the compliance problem that I've demonstrated here? Well, first of all, compliance minimization is trivial by now. And I would say not useful for demonstrating efficiency of new approaches. So if you want to publish a paper where you want to claim that you have a more efficient method, you should do more than just using compliance, because as I said, it's a trivial problem. It has the same sign of sensitivities. Add material where strain energy is high and subtract where it's low. So that's not enough. What problems should you look at? Well, there are many options. For me, I recommend the compliant mechanism problem. So the force inverter that you see in the upper right corner, it's non-self-adjoint. And it has these hinges that create quite a lot of trouble. So that's a good problem. The thermal heat sink problem that we have used in several papers is seemingly extremely simple. It's a thermal compliance, but it's very difficult to introduce a length scale. And so for that reason, I recommend it. And then the stress constraint is you have multiple constraints. You can aggregate it through the stress P norm, but it's also a harder problem, but still manageable. So use some of these examples also as test cases, if not all, when you want to challenge existing approaches on efficiency. And also one recommendation from an old fox in the field, don't invent your own benchmark for known problems. So if you are going to make compliant mechanisms, don't start with your own example. Try to take some of the established one in the literature. So for example, if you don't have the force inverter, which is probably the hardest problem out there, then I would get suspicious if I'm reviewing the paper, because probably your method didn't work for that case. So better use the established benchmarks examples to prove that your method works and is efficient. And lots of potential applications out there, and nonlinearity, stability, or uncertainties. I'm happy to answer more questions on that. At the very end, Joe asked me to be critical. Does the density approach to topology optimization always work? Well, I'm a believer, so yes, I think it always works, but I also admit that we have headaches, some of my students would say sometimes. So we have some issues sometimes with grayscale. And so that could be modeling wise, but it could also be getting rid of the grayscale. And I'm sort of dividing this issue into two areas. There's gray areas. So those are big domains that are gray and which don't get penalized because you're considering a certain physics. And so that requires some playing around and tailoring of the interpolation functions, which can be difficult, especially for multiphysics cases. In worst case, you could actually add some explicit penalization to the objective function, either regularized or non-regularized. Then there's the other issue of gray transition region. So that's the transition between void and solids. The filtering methods that we use have some or require some transition part there. And sometimes people are saying with other approaches that, for example, level set gives crisp and black and white solutions. No, it's because it's the level set that is crisp and smooth, but underlying, if you have a fixed grid approach, then there's also a gray transition region. And in fact, I don't think it's a problem. In fact, I would claim that we need a small gray transition region, because if we want to extract the topology, we don't want a jagged edge to make a contour plot. We want a smooth transition region. So for me, actually, gray transition regions are an advantage, not a disadvantage. And at the very end, for very complex physics problems with very boundary depending physics, like antennas or turbulent fluid, there might be some issues that's common for all fixed grid approaches. I believe that we can still find solutions to everything. Let's see. But alternatively, you would have to switch to some boundary fitted meshes that you can adapt both together with the density approach or other approaches. So that brings me to the end. And I think I'm on time here. So just a number of conclusions. I think gradient-based approaches are extremely efficient and hard to beat. We need filtering to regularize. I'll come back to that next tutorial. Gradients are essential, and they are not too bad to implement. New algorithms should always also be benchmarked on non-self-adjoint problems. And also what I alluded to earlier, I believe we should aim for structures or methods that allow 10,000 in 2D and 1 million elements in 3D. Otherwise, they are not practical for physical use and industrial use. So thanks a lot for listening, and I'm open for questions. And here are some papers that you may use as reference if you want to read more. Thank you.
Thank you so much, Ole. That was really great. Nice with this initial overview. It was even good to get a recap for someone like me. So that's really good. We have a number of questions, so let's get going. So the first one is, do you have any take on using NURBS or BREP interpolation on the sort of the interfaces between the 0-1 densities?
Yeah, so that's sort of going away from an element-based design description to a NURBS-based or something like that. And that can certainly be done if you're still doing it on a fixed underlying grid. Then I don't see the big advantage. I'd rather do various filtering schemes and in that way control stuff. But if you are using also like isogeometric analysis or parametrization, that you actually have the boundary available and you use that, then that would be an advantage for the physics. But then you would have problems with introducing new holes and stuff like that. So I don't really see the very big advantage unless you have some very specific geometry reasons to describe things in that space.
Yes. And the next question is, can you modify the SIMP method for applications outside of solid mechanics? And how would you modify? And maybe you already touched a little bit on that it's possible, at least.
Oh, yeah, we are doing that all the time. I don't know, here I still state, well, this is, there's actually Joe's work on heat transfer. I showed in one of the very first slides our applications in nano optics and solar cells, photovoltaics. So for me, the world is open. If you can model it with a PDE and somewhat efficiently, also preferably with finite elements, then we can apply topology optimization to it. And I think by now it's actually difficult to find a physical setting where nobody has already tried their luck with topology optimization. Some of it is better quality than others, but really there are so many physics where we have been and can do wonders. It's also interesting to see how the field sort of started in mechanics, but it's getting huge. So as I said, in the nanophotonics community, it's huge in fluids, in acoustics, in electromagnetics, it's huge. So definitely, yes, it can be applied everywhere where there's a PDE at work.
Okay, then someone has a question regarding exactly conjugate heat transfer topology optimization. So due to the computational cost on a fine mesh, they want to know if can I run the first iterations on a coarser mesh, then interpolate the density to a finer mesh and continue the optimization to save time. So they state that the absolute value of the filter radius remains the same in this case.
Yeah. Yeah, very good question. So it is a little bit dangerous, right? Because if you start on a very coarse mesh, then you are actually already there introducing a length scale. So let's say if we look at the lower left case here, right, we have this conjugate heat transfer with these very intricate details and stuff like that. And if you had started this on a very coarse mesh, then probably this would never have appeared. You would sort of get led into a local minimum with a very crude solution. So that would be my fear. However, we have tried various other ways. So one thing was together with Niccolo Polini, we tried to make an approach where we started with a simpler fluid model, so essentially with a creeping flow, and then did the initial steps on that, and then went on to the full conjugate heat transfer with Navier-Stokes and stuff like that. So again, it's dangerous, right? Because you may want to get into local optima that turn out not to be good for the real physics. So I would be a little bit careful with these techniques, and maybe you have to bite in the apple and actually run your supercomputer for many of these things.
And the educational codes, can they easily be implemented in Python, or are there any MATLAB specific functions required?
Yeah, well, I think these days, so this is a case where AI is fantastic, right? You just throw your MATLAB code into Copilot or ChatGPT, and it will happily give you the other one. There might be small issues with the graphics, but if you are a Python expert, it should be very simple. And so essentially the 99-line code just requires a linear equation solver, so a backslash operator on LU factorization. That's all what it needs. So yes, very simple. And actually, if you look out there, also look at the review paper, there are references, or search the net for a basic or 99-line code in Python. We actually have one also on the website, the Topology website. So yes, definitely, it's not hard.
Are there existing approaches to solve multi-objective optimization problems without using gradient-free methods?
Well, my recommendation is use gradients, because for these problems here, it's heavy physics, heavy computations, and the gradients are simple to compute. So forget about non-gradient approaches, I would say, for these kinds of problems. It's simply a waste of computing time.
Okay, and so you discussed the differences between SIMP and RAMP. Both curves sort of bend up in a similar way. It is unclear to me what you referred to by convex and concave.
Oh yeah, it gets a bit technical. Let's see, maybe. So it was actually so. Okay, to explain it. So back then, Stolpe and Svanberg, they wanted to solve the topology optimization to extreme to get 0-1 solutions. And then they found that if they used the SIMP approach, no matter how large P was made, they would still sometimes get elements that got stuck in intermediate values. So it was a fairly subtle sort of mathematical exercise. So they showed that SIMP was not purely concave in the overall solution space. Then with the RAMP function, they could show that it was would give you a concave function space, meaning that if they penalized enough, they would always get black and white solutions. So that was sort of their subtle study. As I argued later on, actually, I don't think we want completely black and white. So that would not be the reason for using RAMP instead of SIMP. My reason, or one explanation, is if you look at the gradient at 0, then there's a big difference between SIMP and RAMP. So SIMP has a 0 gradient, whereas RAMP has a finite gradient at density 0. So in some sense, if you have a void domain, then the RAMP interpolation should make it easier to grow material from that void domain, whereas it will seldomly happen in the SIMP domain. So that might sometimes get a better convergence, but my experience is it's not a clear picture of preference for one or the other.
Somebody has asked why filtering is called a regularization technique.
Yeah, so that is this, let's see, where can I, I think I have to go backwards. So, no, wait a second, we are going the other way. Sorry, I'll just get to it. So this is sort of the original problem, right? So if we have a problem and we optimize it on a finer and finer mesh, then we get finer and finer solutions. So in that way, the problem is mathematically ill-posed. So you don't have a solution. If you have a finer mesh, you get a finer structure. And so then by regularizing, we mean that we somehow put something into the formulation such that we get convergence. And there are two ways of regularization. One is this, what we call relaxation, where we, instead of having one density at every point, then we say in every element there is a microstructure. Hence, we have already taken this finer and finer and finer grid into account when we parameterize the problem. So that's one way to regularize. And in that way, we don't get better solutions if we make finer mesh, because it already has a microstructure in the mesh. So that's what I'm going to discuss in day 3. The other regularization approach is restriction, and that's where we restrict these rapid variations by different means. And here I mainly discuss the filtering techniques, which can be seen as a low-pass filter that we kill all rapid variations, and in that way we also get a problem with a solution, and we have thereby regularized the problem.
Yeah, quite a lot of questions. They keep coming, but I see one I really like. So, what are some mistakes you see beginners make when they enter into density-based topology optimization?
Yeah, first of all, thinking that it's too easy. It is, if you want to make something new these days, it's actually not easy anymore. But then I would also refer you to this benchmarking paper, because that's sort of a result of my many years as a reviewer, reading all kinds of stuff by often people new in the field who make various claims of convergence or improvement compared to existing stuff. Or they, for example, say, see here, I have a method that gives much better compliance than those produced by the 88-line code. But then they are comparing a filtered design and a non-filtered design, which essentially are not comparable and stuff like that. So I would say that this paper pretty much lists all the sort of beginners' mistakes, and sometimes also people long in the field who make these mistakes. And I would also say it actually corrects some of my own mistakes from very early days. So for example, one point here is the boundary conditions. We have always been violating basic finite element theory by having point supports and point loads on our structures. That's a really bad finite element style, and means that the finite element analysis never will converge. So I'm, for example, advocating that we always have a distributed support, still free to rotate, and we have distributed loads and stuff like that. They should be obvious, but nevertheless, that's not the case. So I think really I would advocate, read this paper, and if you're still in doubt about anything, then give me a call or send me a mail and ask. This is sort of the place to go.
Yes, and of course you just say when you are done, because we have 13 questions left, and I think that might be too much. But so one person has asked, do you suggest a mix of density and level set based methods SIMP for its fast solution and then level set for the crisp boundary?
Yeah, no, because I would say that that SIMP has, or I don't call it SIMP because SIMP is really just a small part of it. So a density approach or level set. And actually, as I will talk about next week, we do get very crisp as we like designs by the various robust and projection approaches. So I wouldn't say that level set methods have an advantage there. It's not because I'm saying don't use level set, but just don't see that it has a specific advantage there. So the case where the level set method is strong is if you actually adapt the boundary with the finite element mesh. So that is where, and there are some works by various Frenchmen and others where they actually adapt the mesh. But otherwise, the level set method has the same things. It's working on a fixed grid, or by far most of the level set methods, and they just use the level set function instead of the filtered field to control the density. So I don't see a big difference there. So I guess the answer is no if you do level set on a fixed grid method, as 90% probably are. But possibly yes if you actually have a mesh that follows the boundaries of your design.
And then there are two questions sort of about time-dependent stuff in each their way. So one is that is the adjoint gradient for dynamic problems where you use a little bit more complicated time integration schemes like generalized alpha and so on. Is that more challenging for the adjoint? And the other one is sort of if you could touch upon these checkpointing and other methods to sort of reduce the cost of those.
Oh, okay, that gets very detailed, I would say. And to be honest, I haven't myself done very much on the transient problems. Probably a good one to ask would be Niels O. You could contact him and get more answers there. But so obviously, if you have some very complex time stepping schemes and with local adaptation and stuff like that, you may not want to actually go backwards through the same adapted time steps, but only take the sort of real time steps and stuff like that. So there are different techniques. Another thing in transient analysis is that you have to save all the forward time steps to make the backward time step. And that's where it becomes extremely expensive and also CPU and memory intensive. And so this is why people do this, what is it called, milestoning? It's not milestoning, what is it called?
Checkpointing.
Checkpointing, yes. So checkpointing that you, in the forward analysis, you save certain time steps. And then when you have to do the backward analysis, you go back to the last time step, do your forward analysis, save the steps, and then do your backward time stepping. And in that way, go back to the next stone here, and then redo the forward analysis and stuff. So it's challenging, and so in that way you could say it's actually 3 times the number of analysis because you have to redo the forward time stepping. So it does get more complicated, but nevertheless, if you look out there, there are amazing works of transient problems where people manage to get extremely good accuracy and very efficient structures and stuff like that. So I would suggest to contact or first look up some of those advanced topology optimization transient problems or papers, and possibly also contact the authors if you have specific questions there.
There are, still, so, but I really like this. So maybe we take 2 more questions and then that has to be it for today. But what is your preferred approach for tuning these different parameters? So the penalty parameters and the various ones that come into the filters and so on. I think that's something everyone finds a little bit difficult. So do you have any tips on that?
Yeah, so the less the better. So I sort of have the principle that in the outset, use p equal to 3, use the standard settings in MMA, so possibly with slightly less aggressive asymptote updates. And if it doesn't work, then probably your physics is has a problem. So either you didn't normalize things well, or somehow your physics is ill-posed or stuff like that. And so I don't start messing with MMA parameters for specific problems, and I preferably don't mess with the penalization exponent. There might be cases like in material design that really like grayscale, so you need a slightly higher P. But usually I discover that if the MMA optimizer is behaving weirdly and not delivering, then it's because I fed it some way garbage. Either the numerical model, the finite element model, is badly scaled, or I forgot to normalize in good ways and stuff like that. So when you read papers of people talking about optimizing hyperparameters and stuff like that, I'm not a fan. I think you have to go back and look at your original problem and see if you scaled it correctly and if the physics is well scaled.
And then maybe the last question here then for today will be how can one address the issue that the starting point often is sort of very impactful for the convergence and the result?
Very good question. Actually, I have an algorithm coming up in my lab, or actually in my own computer here, that makes things less sensitive to starting guesses, but I will come back to that not in these tutorials. But it's a good question. So I try a couple of different starting guesses. Sometimes you run your optimization and you're wondering, why didn't I get the solution I expected? So then you could try to draw the solution you expected and use it as a starting guess. And then if it goes back to the one you didn't expect, well, then probably you have the right solution and your intuition was wrong. So usually a couple of different starting guesses at different densities and maybe a couple of different filter sizes if it's not really for the physical realization that you use the filter, and you tend to get up to good solutions. An exception is in wave propagation problems, and there we haven't really found a good solution, because there in wave propagation problems, the original wavelength depends very much on the density of the initial design, and there you can really get stuck in different solutions. So there again, realizing that that's the case, then I would start like with 5 different density levels as starting guesses and go from there, and probably one of them will be good. So I'm generally a well set up optimization problem that makes use of consistent filtering and stuff like that. It's my experience that they are not so prone to local minima, as long as the original resolution is fine enough.
Yes, thank you very much for everything, Ole, and thank you for the last 136 that stuck around until the end here.
Yeah,
sorry
it's
for
really
the
impressive.
last, yeah, sorry for the last few people with questions, but I tried to prioritize the most relevant ones. Some of them you can ask the next time where they are more relevant, and so the next webinar will be on the 11th of February, and you can sign up if you haven't already. Our website should be updated soon, but at least on the website you can go in and you can fill out our Google form to get on the mailing list, and you will get the new links on there. Or you can try to find me on LinkedIn. There are also the links for all 3 of the webinars. Okay, yeah, thank you very much.
Thank you also to everybody for listening. I hope you enjoyed it.